Let's look at higher order derivatives. There's not really too much of this in your textbook, so you'll want to look in the math packet for some example problems. The first derivative we call velocity, the slope, okay, all of that means the same, where if we take the second derivative, that's acceleration, the third derivative is called the jerk or jolt and shake. Actually, the second derivative is kind of nice to know because if you're looking at the rate of, say, a profit, and you can see that it's increasing, well, the second derivative could tell you if it's starting to increase very quickly or if it's starting to slow down, something like that. The third derivative certainly could say, something happened within the market and it caused the shakeup, for something to change. And so these are all very nice to know in the business world. So this is probably the best example. It's probably not much businessy, but will help you understand the different derivatives. Is if s of t is the position function and you're on a roller coaster, then s prime of t, the first derivative, would be the velocity of the roller coaster at a particular time. The second derivative would be if it's speeding up, slowing down, your acceleration. And then the third derivative, what happens on a roller coaster. How do they stop the roller coaster? It's never a nice slow stop, right? It's a very abrupt change in acceleration. And again, we're going to relate these to the business world to say, well, is profit increasing or decreasing? We could find that by the first derivative. How quickly is it increasing or decreasing? And has something happened to cause an abrupt change in how fast it's increasing? Okay, let's look at a graph and see visually the interpretation of the second derivative. If your first derivative is negative, remember that slope, so that's decreasing, and then it goes to 0 and then it increases. When this happens, actually your second derivative is greater than 0. And in a way that hopefully should make sense because you can see that you're starting to accelerate as you make that turn. And so our second derivative would say our graph is concave up. If our second derivative is less than 0, that would say our graph is concave down. And of course, this is kind of nice to know these things because if the first derivative can tell you if your function's increasing or decreasing, positive or negative, the second derivative can actually tell you how fast it's increasing, since remember, it's telling you the acceleration. If I have this p of t as a function that represents population size, what I want to do is go through, and this is in your math packet, and interpret what this would mean. What would p prime, if that's positive, and p double prime, so the first derivative is positive, the second derivative is negative, what would that mean? Well, if the first derivative is positive, we're increasing. The second derivative is negative, so it's starting to turn concave down, so the population is increasing, but at a slower rate. If we had both the first and second derivatives were positive, then we would have increasing, but now it's starting to increase at a faster rate because we said when the second derivative is positive, it's concave up. If they're both negative, the first and second derivative, then negative derivative says it's decreasing, but now our second derivative being negative, it's decreasing at a faster rate. And then finally, if the first derivative is negative, we know that's a decrease, but the second derivative now is positive, means it's starting to decrease at a slower rate. So how you find these second and third derivatives, remember when you find the derivative for a particular x, meaning for x equals 5, then when you plugged in your value and you found the derivative, you got a slope. But if we wanted to find the derivative for all f of x, we get another function. So we take that function, we take the derivative of again, and that gives us another function. And that's our second derivative. And then again, and so on. And we can continue to do this until you'll see you'll end up with a constant eventually. So if I want to take the first, second, third, and fourth derivatives of this following function, the first derivative, I bring the 4 down, subtract 1. 3 times 3 is 9, subtract 1. 2 times 2 is 4, and then my 8x is 8. Take the derivative again. 3 times 4 is 12. 2 times 9 is 18, and then 4. Take the derivative again. 2 times 12 is 24. 18x is 18. And then finally, the fourth derivative would be just 24, because this, of course, constant goes away. So this is how you would take each individual derivative. Even if I wanted to take the first, second, third, fourth of a quotient rule, well, I would simply do my quotient rule. So the first derivative, I leave the bottom alone, times the derivative of the top, minus leave the top alone times the derivative of the bottom. And so nicely things cancel out, and I get this. Probably the easier way is to have left it as negative 2x to the negative 2, because then I would take negative 2 times negative 2, and that's how I get positive 4, and subtract 1. So leaving it in this format is probably a little bit easier to see. And then negative 3 times 4, negative 12, I get negative 4. Negative 4 times negative 12, I get negative and negative, I get a positive 48. And then each one of these, notice I'm subtracting 1. Okay, so again, I probably, this first step here, would have rewritten this as negative 2x to the minus 2, because then it makes it easy to fall down the line. All right, let's let you practice a little bit. Find the second derivative for this. As you can see, you can either multiply it, FOIL it out, or you have a product. And so what I would do is pause this. Now that you've come back, check your answer. If you did not get this answer to find the second derivative and you can't figure out how to get it, then email me. Okay, so I want you to do a little practice. Let's let you do another one. Find the second derivative for this quotient, and there's your answer. So if you go through the steps of the quotient rule twice, right, because this is the second derivative, you should get this answer. All right, the population of a city T years from now is predicted to be this function. Evaluate the population at 10 years, evaluate the first derivative and second derivative, and tell me what it means. So P of 10 says just simply take your original function and plug in a 10, and you should get 200, which is in thousands. So this would be the actual population 10 years from now. P prime of 10 says take the derivative. So 3 times 0.25, 0.75, 2 times 3, 6, 5, and then plug in 10. And this is a rate. It's positive, so it's increasing. And it says the population will be increasing 10 years from now by 20,000 people. Find the second derivative. So I'm taking the derivative of this, 2 times 0.75, my 1.5, my 6. I plug in 10 for the second derivative. And because this is positive, remember, if it's positive, that says the population is increasing at a very fast rate. Because if it's positive, it means it's concave up, so it starts to take off.